Well, hopefully that gave you no trouble. It was just a fairly simple little piece of trigonometry. The key is that XO here is the same as XC, and we just have to look at this triangle. We see the hypotenuse is R. XC, which is the same as XO, is the side that's adjacent to this angle, and so the answer is that XO must be R cos theta. If we just knew how theta varied with time, then we would have this as a function of time. But that's easy because this is uniform circular motion. So this thing is going equal distances around the edge of the circle in equal times, which means this angle is increasing at a constant rate. And we know what that looks like as a graph. Whenever you have something increasing at a constant rate, that means you have a linear graph. And so our theta versus time graph must just be a straight line. And we can define things so that at t equals 0, theta is 0. We're just saying that t equals 0 is when this passes through this point. And now look what that tells us. In a time equal to the period, this goes around a full circle. Now, it's tempting to write 360 degrees here, but it's actually more convenient to work in radians. And hopefully you know that a full circle is 2 pi radians. And so what we have now is a line where we can see that theta is the slope of this line times t, and that slope is just a rise over a run, and that rise is 2 pi, and that run is capital T, and so there we have it. Theta just goes like this, and so that is our XC. It is R cosine 2 pi over the period times T. And we know that that's the same as XO. But for XO, we don't want to write R. We want to write this all in terms of properties of that motion. But we know that the radius is the same as the amplitude. And so there is our final relationship, and we'll use this over and over again. This gives us, at any time now, we can say what the position is of the oscillator. So I'll just finish off this lecture by pointing out that we now have two different definitions of simple harmonic oscillation, or ways of recognizing it. The first is if there's a linear restoring force, then we know this is something that is like a mass on a spring, and so it will execute simple harmonic oscillations. But the other is if you see sinusoidal motion. Okay, so if your data looks like this, then you know that's simple harmonic oscillations as well. And the presence of either of these, a linear restoring force or sinusoidal motion, means that what you are dealing with is simple harmonic oscillations. You can take either one of these as a definition of it. And you can show, we haven't really shown, you need some calculus to do it. You can show that the one implies the other. If you see a system and you analyze it and find that it has a linear restoring force, then you can bet your boots that when you look at its position versus time, it's going to be sinusoidal. And likewise, when you see sinusoidal motion, you can bet that the culprit responsible for that sinusoidal motion is a linear restoring force.